In this video, we're going to study the Sieve of Eratosthenes. What is the Sieve of Eratosthenes? Well, it's an algorithm that allows us to determine the prime numbers that are less than or equal to a given positive integer n. And it's actually amazing to think that this algorithm's over 2,000 years old. In this video, we're going to talk about it. We're going to implement it in Python and talk about some optimizations. Why don't we begin just by talking a little bit about who Eratosthenes was. He was a Greek scholar born in 276 BC. He was a man of learning in many fields, including mathematics, geography, astronomy, and music. He held the position of the chief librarian at the Library of Alexandria, and he's best known for being the first person to calculate the circumference of the Earth, and his calculation was remarkably accurate. He created the first global projection of the world, incorporating parallels and meridians. And he calculated that there are 365 days in a year, and every fourth year there'd be 366 days. So why do we call this a sieve? It's basically the goal of the Sieve of Eratosthenes is to separate the primes from the composites. And that's kind of what a sieve is used for in baking. You run the flour through the sieve. It isn't quite the same though, because I think in baking, eventually all the flour passes through the sieve. But for what we're doing, it's not like that. There will be numbers that remain and numbers that fall through. The numbers that remain will be the prime numbers, which is the numbers we want. And the numbers that fall through will be the composite numbers, the ones we don't want. So that's the context of the word sieve here. All right, let's begin by describing the algorithm. Let's take n to be a positive integer, and we'll define s to be the set of positive integers from 2 to n. We'll define p to be 2 as an initial value, and then we're going to repeat this cycle right here. And what is that cycle? Well, we first look to see if there are any elements in the set s which are greater than p. And if there's not, then the algorithm terminates, and the set S will be the set of primes. But that's not going to happen until the end. We're going to have to go through this loop several times. And what do we do in that loop? Well, let's say that there are elements in S which are greater than P. The answer to the question is yes, so we follow this path. What we do then is we remove all the multiples of P from S, but not P itself. Technically speaking, P is a multiple of P, but when we speak of removing the multiples of P here from S, we mean every multiple of P, but not P itself. Then we look at S to see the elements that are left, and the smallest number that's in S is the new value of P, and we redefine P to be this new value. Then we repeat the process. P is the maximum of S, and then we know that we're all done, and S consists then precisely of the set of primes. So we'll do an actual example in a second, if this is not clear. So why does this algorithm work? Well, we never remove any number from S that's prime, because we're always removing multiples, right? And that means in the final result, S contains every prime number. And then maybe the next thing to notice is that since every prime remains in S, at some point that prime was the value of P, which means every multiple of that prime was removed from S. And having all the multiples of all the primes in S removed, that means S must consist only of the primes. You could provide maybe a more rigorous proof using finite induction on P, but let's not go down that path for this video. Now, a little optimization we can do is once P becomes larger than the square root of n, then necessarily all of the numbers that remain in S are prime, and we can actually stop them, and we don't have to go any further. And the proof of this is in the following proposition. So this is a little bit separate from the Sieve of Eratosthenes. This is an important result just on its own, but let's talk about it because it's what allows us to do this which allows us to stop once P gets to be larger than root n in the sieve. So this proposition says any composite number n must have a prime divisor p where p is less than or equal to root n. So to prove this, why don't we use a proof by contradiction, which means we assume the opposite is true, and then we argue to a contradiction, which in fact proves the result. So let's suppose the contradiction that n is a composite number, and it has the property that every prime divisor p is greater than the square root of n. Let's show that this is impossible. Well, since n is composite, we know we can decompose n as a times b, where both a and b are integers greater than 1. And we know that any number has a prime divisor. Any number greater than 1 has a prime divisor. The prime number might be the number itself, but that's fine. So that means a and b, being bigger than 1, each have prime divisors. So let's say that p divides a and q divides b. Now, we have the contradiction right now because n, which is equal to a times b, but since p divides a, we know a is greater than or equal to p. Since q divides b, we know b is greater than or equal to q. So when we write here n is a times b, we know that it's greater than or equal to p times q. But by assumption, since a and b divide n, p and q divide n, and so those prime divisors must be bigger than root n. So p times q is strictly larger than root n times root n, which equals n. And then we see we have a contradiction because it's saying here n is strictly greater than n. That's a contradiction, and that in fact proves the result. So we know that once p gets larger than root n, that every other number beyond that has to be prime. So in order to make this clear, why don't we do a little example, and let's find all the prime numbers up to 100. And then it'll become more clear the way this works. So to start, let's just write down all the positive integers from 2 to 100. It doesn't matter how you arrange them. You can do it in any way. We start the algorithm by letting p be equal to 2, right? The first prime number. Then we look at every multiple of p, but not p itself. They're all listed in red here. And we remove every one of those elements from the set S. So now we look at the set S and we ask ourselves, what's the next number in here which hasn't been removed? Which the next number is 3, right? That's larger than the current value of p. So that means our new value of p is 3. Then we repeat ourselves, right? We look at all the multiples of the prime number 3. Now, some of these have already been removed, like 6, and some of them have not, like 9. So any number that hasn't been removed yet, we're going to remove it right now from S. So currently S is the numbers that haven't been crossed off. The next number in S that we haven't dealt with, that's the smallest one is 5, right? 5 is the next number bigger than p. And so that is our new value of p, and we just keep repeating ourselves like this. All the multiples of 5 are these ones. All these have already been removed, but some of these haven't, so let's remove them. The next number beyond 5 here is 7. That's the next one that hasn't been selected, so that's our next prime. We look at all the multiples of 7. Here they are. Any one that hasn't been crossed off or removed yet, we're going to remove it right now. And now something interesting happens. The next number is 11, right? So p equals 11 now. Now notice this, that the square root of 100 is 10, right? We finally got to a prime p that's bigger than the square root of 100. In other words, 10. So since 11 is larger than 10, 11 is larger than the root of 100, that means we can stop. We actually have all the primes now. The rest of the numbers in the list, like 67 and 71 here, 17, these are all necessarily prime. And we terminate the algorithm now, and here we are. The set of prime numbers from 1 to 100 are determined. Now, before we go on, let's just mention another little optimization we can make, and that's this. You see, the way it is now, once we find a number p, we remove all the multiples of p, starting at the next one, which would be 2p, right? 2p, 3p, all the way up. But in fact, we can start, instead of starting at 2p, we can start at p squared and then remove all the multiples from that. The reason for this is, in fact, that proposition we proved before. Because why don't we suppose that there's some number m between p and p squared that hasn't been removed or crossed off? Well, we know that m is going to have a prime divisor q, where q is less than or equal to root m. That was the proposition. But if we square root both of these here, we find that root m is less than the root of p squared, which is p. So root m is less than p. So q is less than root m, and root m is less than p. So q is less than p, which means that m has the prime divisor of q, and q is less than p. But if q appeared before in the list, m would have been crossed off because m is a multiple of q. So I hope that convinces you that we can, in fact, start the crossing off process at p squared. And that's all this small little change I'm making right here. If p is not bigger than root n, then we remove all the multiples of p, that's the same, but instead of starting at 2p, we start at p squared, and then we go up by p after that though. So why don't we try to implement this in Python now? We're going to give several different approaches to this just to show the different ways of doing it. But the idea is going to be the same for each version. We're always going to define a list P of n plus 1 Boolean values. And for any I between 2 and n, this list will have the property that Pi is true if and only if I is a prime. So here's our first version of the sieve. We begin by defining P, like we said, to be an array or a list of n plus 1 Boolean values. And at the beginning, we assume they're all true. And in the end, true means prime. So it's kind of like at the beginning, we're assuming all of the values are prime. If we're really particular, we might insert inside here P0 equals false and P1 equals false, because 0 and 1 are not prime, right? But it doesn't matter because we're never going to talk about those values of I anyway, so I'm just going to leave those off. But here's the main for loop here. Remember the very first version? We went all the way till the end. We didn't do none of this root n stuff. So I goes from 2 all the way up to n. I have to write n plus 1 here because in Python range, it'll make this one less. So this really just means I starts at 2 and goes up to n inclusive. And if Pi, so if I is prime, then we start at the next multiple of I. M is for multiple here, kind of. After I, what's the next multiple? I plus I, right? And then this is just saying, well, the multiple is less than or equal to n. Put Pm to be false because m is a multiple of some number. It couldn't be prime, so we put it to be false. And then we increment the multiple to the next multiple, and we just keep cycling through that while loop until our multiple is larger than n. And then we go to the next value of I, and we search for the first one after that that is true, which means that's the next prime number, right? So we can kind of see how that works. And then we just use this nice little technique here that we're going to basically convert our list of Boolean values into a list of integers, because kind of as our final output, we don't want a list of Booleans as our output. We want a list of prime numbers as our output, right? So we're going to take all the i's between 2 and n plus 1. Notice we ignore 0 and 1 here because we don't care about them. So this goes from 2 to n. And whenever Pi is true, which means I is prime, we're going to throw that I into a list. And that's a nice way of returning the list of prime numbers from the list of Booleans. So this is the very first flowchart algorithm that I put up. This is exactly implemented in Python, okay? Now, if you remember, we talked about the next optimization, which was instead of going all the way to n plus 1 here, why don't we just go to the square root of n, including the square root of n? Since I'm including the square root of n, I'm putting a plus 1 there. Now, the only change between the one I just showed and this one is that I'm just putting this square root in, and It's a small optimization. Notice we still have I plus I here and all that. So that's fine. And then we could go even further where we talked about starting at I squared, right? So on this one, we're going to the root of n. And instead of starting at 2i, we start at I squared. And that's even a little bit more of an optimization, right? So let's take this a little bit to the next level now. And let's use the slice notation of lists for Python. Here's a little diagram of what's going on, kind of. We have a prime I, and then we look at all the multiples of I that are below the n, right? And why don't we try to come up with a formula for k? K has the property that k times I is smaller or equal to n, but the next multiple of I, which would be k plus 1 times I, is going to be strictly larger than n. And this is how we're going to define k. And let's try to run through this and solve for k. Let's just start by multiplying these brackets out. So we get ki plus I. Let's subtract ki from all these sides. So we get 0 is less than or equal to n minus ki is less than I. Let's subtract n now from everywhere. So we get negative n. When I subtract n from here, I just get minus ki, and then I becomes I minus n. Now let's multiply everything by negative 1. So all of those get hit by negative 1. I minus n times negative 1 is n minus I, right? And notice when you multiply by negative, these inequality signs have to flip, right? Now to go from here to here, I've just flipped everything over. I just put the n minus I on this side and the n on this side, and the inequality signs will flip then as well. Then I divided everything by I. And notice here, I divided by I is 1. So here we get a nice form. N over I minus 1 is less than k is less than or equal to n minus I. You know, it's a property that if x is any real number and k is an integer where x minus 1 is less than k is less than x, that means k is the floor of x. So this n over I, we don't expect that to be an integer. But k is an integer, it's a positive integer. And we've solved for k here. K is the floor of n over I. We'll use that in code in a second. And also notice these are the multiples we're removing, right? How many are there? There's k minus 1 of them, right? This is 1, 2, up to k. We're not removing this one, so that means there's k minus 1 multiples where k is equal to the floor of n over I. So why am I talking about this? Here. We're going to avoid that while loop. We're going to just say whenever we find a prime, we'll take k to be the floor of n over I. That's what we just proceeded to calculate it there. And then let's take a look at this. We start at 2i, and then we go all the way to the end of the list. That's why there's nothing there. And from 2i, we go up by I every time. So we start at 2i, and then we go up by I until the very end of the list. And what do we define that slice of that list to be? A whole bunch of falses, right? This is like crossing off a whole bunch of numbers from the list. How many are there? K minus 1, right? That's why I wrote this here, k minus 1. So k is defined as the floor of n over I. We're removing k minus 1 multiples. They all become false, and we get that. And then in the same way, we return a list of integers from the list of booleans. And why don't we, remember how we said we don't really have to start from 2 times I? We can start from I squared. Why don't we think about that for a second? So if we start from I squared, and then the next multiple would be I squared plus I, and then all the way, eventually we reach the last multiple, which is I squared plus ki. That should be less than or equal to n. And then the next one, I squared plus k plus 1i, should be strictly larger than n. And very similarly, we can solve for n here. How does that work? Well, we multiply the I across. We subtract ki. We subtract n. We multiply by negative 1. We flip everything over. We divide by I. Over here, I minus I is 1. And so here we have the same situation. Imagine this is x, and this is x minus 1. X is some real number, rational number, and k is in between those values, and it's a property of the floor. That means k is the floor of n minus I squared over I. And that's nice. So we have a formula for k. And how many multiples do we have here? Well, this time we're including this one. And this corresponds to k being 0. This is k being 1, and this is k being k. So in total, we have k plus 1 multiples this time. And so this k plus 1, along with this formula for the floor here, is going to play a role in this little version of the sieve. We start the same way. We're going just up to the square root. Whenever we find a prime, instead of doing that while loop, we're just going to define k to be that number we saw there, the floor of that. And then we're going to take a slice of the list, starting at I squared this time instead of 2I. We're going to go all the way to the end, and we're going to go up by I every time. And we're going to make all those false. How many falses? K plus 1 of them, right? That's why I'm talking about k plus 1 right there. So these are the versions of the sieve I wanted to talk about. And why don't we just put all those into a Python environment and first of all test that they work, and then second of all, see which one's the fastest. And that'll be the next thing we try to do. All right, we're inside of a Python environment, and we have all of the versions of the sieve we talked about listed. Here's version 1, 2, all the way up to 5. And we're going to let n be 100, and we'll call each of the versions on that value of n, and we'll print off the results. So we're hoping to see the list of prime numbers between 1 and 100 printed out for each version, so 5 times. Yeah, and we have that, so that's good. So now we would like to test the efficiency of the time it takes for each of these to work. So why don't we import time? And let's just do something simple like this. We'll define t0 to be time.time. And then at the end of the calculation, we'll put t1 to be time.time. And then the time it took to run the routine is just going to be t1 minus t0. Why don't we run that? And we get a time value. So let's put this code in each one of these routines. What we'd like to do is to test the times of each of these versions. And for that, we don't need to print out the results. So we'll get rid of these print statements. All we care about is these print statements here, which print the times, the time that the calculation needed to take place. So when we do with 100, we get very small numbers. It's hard to see kind of what's going on. Let's raise the number of primes. All right, so we get some interesting results here. We see that version 1 takes a very long time compared to version 5. Version 4 is slightly longer than version 5. We see the improvement from version 2 to version 1 when we stopped at the square root there. And version 2 to version 3 is when we started at I squared for version 3 instead of at I. So at 2I. So that shows that probably version 5 is the best one. And it's kind of interesting to see the amount of time savings when we use the list slice notation, how that really speeds things up to a new level. I just wanted to show you a web page here. It is definitely on what we're talking about here. I'll just show you this post here. Let's take a look at this code. This is understandable to us based on what we've just done. So notice it's kind of the same idea. They define an array of true or a list of true values. They're only using n of them. Notice that they're skipping the even numbers, right? They're going up by 2s and they're just starting at 3. 2 is thrown in at the end. And they have n minus I squared. And then the 2i plus 1, that's coming in, I think, because they're ignoring the even numbers. So why don't we test this and just see the difference, if that can beat it at all. Let's forget about versions 1 to 3 and just do 4 and 5, and we'll do this one here. And why don't we calculate the time of this one as well to see if it is better. All right, let's see what happens when we run this. All right, we see that version 5 beats version 4, but the one we just grabbed from Stack Overflow does a much better job than our version 5 even. Maybe that's because they're skipping the even numbers. But other than that, it's the same. Notice here they're going up by 2i. They're starting at I squared, just like us. And that optimization, that further optimization, definitely showed some results there. So if you wanted to go further on that web page, you could even beat this time, I'm sure. So that web page explores this topic much more deeply, but I think we'll stop here, and this will be our final code for the Sieve of Eratosthenes.